Welcome to the NCTSPM seminar. Today we have one of our own, Dr. Laurie Garrow, who will be discussing some activities. Dr. Garrow received her Ph.D. from Northwestern University. Has worked for 5 years, I think, at United Airlines, working on there. Her dissertation was related to, of course, airline usage, and it won a award from the Informs for outstanding dissertation. Since then, she's been the award recipient of an SF Career Award. She won the VP Junior Faculty Teaching Award here at Georgia Tech by SEAL. And she was also the recipient of the ASCE Huber Award of ASCE-wide. She's written a textbook on discrete choice modeling for airline applications, and she recently served as president of the Transportation Science and Logistics Society of Informs, as well as numerous other. She's currently co-chair of the PRB committee as well. So without further ado, Dr. Laurie Garrow.
Thank you, Dr. Rogers. So today I'm going to talk about a project that I worked on with various individuals, and specifically looking at estimation of airline itinerary choice models using a new ticketing database that we had. Ziron Chen is a master's student in computer science who's been working with me on this. At the end, I'll show some programming he's done. Matt Higgins is an economist in Scheller who's been, again, very instrumental in helping us through some of the technical issues. And Jeff Newman is a research engineer of mine who's based in Chicago. And a lot of this work draws on a doctoral student, a former doctoral student, Virginia Merkin, who got her Ph.D. at the University of Liège in Belgium and is now at EPFL. And I had helped co-advise her. So recognizing a lot of us may not have a good understanding of how an airline works, I want to start by reviewing network planning models in aviation and then go through the traditional outline, what's our research objectives, data methodology, etc. So network planning models. I think as civil engineering students, we're used to thinking about urban demand models, right, in terms of the four-step process, even though there's more advanced. But what do we basically do? We have to figure out how many trips there's going to be, trip generation, figure out where they're going to go in the network, trip distribution, assign them to the network, generation, distribution, assignment, so looking at that. We do the same thing in aviation in terms of looking at these network planning modules as more modular. Network planning models are used by airlines to figure out schedule profitability. I'm Delta. I need to figure out how many aircraft I want to buy, what size, where am I going to fly them. If I have different partners that come to me and say they want to code share or sell tickets on me, which code share partners do I look at? So these network planning models are very strategic in nature, and they're used to make, as I call these, mid to long-term decisions. Like we see in our four-step process, we have various sub-modules. I have a schedule. So first thing I do is that I figure out if I have a schedule or legs, how to put those legs together to figure out the paths or itineraries that my passengers are most likely to take. Once I have a set of paths and the quality metrics for that, I can figure out the market share. So how many passengers or what percent of the passengers are going to take the nonstop versus the connection at a certain time. After this, typically it's done the market size. So how many people are going to fly in a given OD pair. This can change over the decades, so again, we tend to view this as separate. And then in airlines, we have this issue where, unlike traffic, I got to make sure that my people aren't flying on the wings. Right? So when I allocate demand to my itineraries, I have spillover capture. I got to make sure that basically I'm not putting more people on a plane than there are seats available. So we have spillover capture models, and then finally we look at the revenue and costs. So what I'm going to focus on here is really the second one, which are these market share models. And figuring out, again, given you have your itineraries in the system, what's the probability that a given individual is going to select one of those itineraries? So various things are used in practice. One of them that we should have all seen by now is the discrete choice model. So the itinerary choice model is one of the core models that's used to basically look at how individuals are making trade-offs among the different attributes. The discrete choice models are really good at looking at these trade-offs. How am I trading off cost, time, equipment, a whole bunch of different factors. right? We've been deregulated since 1978. I would argue if I asked you what are the factors that individuals use to choose taking MARTA versus driving, you could list them, right? Same thing in aviation. At this point, I would argue we have a pretty good sense of the factors that influence itinerary choice. Again, some of them are listed here. Departure time, maybe the departure day of the week, different preferences depending on if I'm leaving Monday versus returning Thursday. Equipment type, a lot of people don't like flying those prop propeller planes. Carrier, we're in Atlanta, so I would argue a lot of us have our Delta frequent flyer memberships. In the core though, if you think about it, price is probably number one, right? When we go to the website, we're students, price is number one. So one of the things that I thought was interesting when I went and I spoke to some of the airlines about their itinerary choice models is that some of the carriers don't include price in the model. Let me repeat that again. Some of the carriers do not include price as a factor in the itinerary choice models. Okay, well what is the problem? Why is this the case? When our data, we have what I call as a fundamental problem. Anybody book their tickets yet for Thanksgiving? Yeah. Did you pay more or less than you thought you wanted to? It's always more. It's always more. Why is it always more at Thanksgiving?
Because it's most popular travel time.
Because it's a popular travel time. So the fundamental problem is, let's look at these three flights. Which flight has the highest price of the three listed? The one with the lowest demand or the one with the highest demand? Highest demand. So we have this fundamental problem where if I just run an equation where I'm predicting demand as a function of price, what's the model going to tell me? Well, heck, raise your price. I'm going to get a positive coefficient. It's going to tell me, raise your price, because when you raise price, more people come. Okay, well that's not causality, right? That's, that's not exactly what's going on. So we have this problem of the simultaneity occurring of demand and supply, where basically we see these high prices at times of high demand, and as a result, it sort of screws up, if you will, the underlying airline price coefficient. So it's historically been very difficult for us to put price in models because we haven't been able to get realistic estimates. So what we wanted to do is we wanted to see if we could attack this problem, if we could estimate models that account for price endogeneity. So the simultaneity problem is also referred to as price endogeneity. And then we got lucky in that Airline's reporting company basically gave us at Georgia Tech a database of airline tickets. This is significant because it's the first academic partnership between ARC and a university. And what it does is it allows us to look at all of the tickets that have been purchased in the U.S. through travel agencies, both online like Travelocity and then offline, like here at Georgia Tech. If you take a business trip, you can go through a dedicated brick-and-mortar travel agency. But we were able to basically look at this data set and, if you will, get the detailed information we needed. So we use this data set. The data we have that the results are going to come from are this ARC ticketing data. We picked a month of departures, May 2013. We restricted the analysis to continental U.S. markets, included simple one-way and round trips with at most 2 connections. That was about 87% of all of the data, so that's a pretty large chunk. And then we have this issue where we have fares that are less than $50. A lot of that are employees traveling, non-rev. And then charter flights. So like, we had the baseball game last night. Charter flight is if the Cubs are going, to a different ballpark that the whole Cubs team gets on. So it's a charter flight. They just basically buy the whole aircraft. So you get these really ridiculous prices of like $25,000 or $250,000, depending on how many people are traveling. Not realistic, so we got to screen those out. So at the end of the day, 1 month we've got 10 million tickets that meet this criteria. So really a large, big data analysis going on. So I said before that we tend to know the variables that we think influence itinerary choice. Carrier preferences, that's like we're in Atlanta, so that you prefer Delta versus American versus Southwest. Marketing relationships, and Brent, I'm going to talk about price, departure time of day preferences. Elapsed time is just how much time you're in the air. So ground, they call it wheels up to wheels down. Number of connections, so 1 connection, 2 connections, and a direct flight indicator. A direct flight is basically you use the same flight number, and in theory you don't have to get off the aircraft. So if you've flown Southwest a lot, they use a lot of the direct indicators. So it's a little bit better if you want to do that than a connection, which in theory you're not getting off the plane, and you can have smaller connections. Okay, so the red ones, marketing relationship. Anyone buy a ticket and think it was like on Delta and then show up at the airport and realize you're actually flying KLM or Air France? So what's going on there? That's a different marketing relationship. So in the airline industry, carriers allow other carriers to sell seats for them. So you have the operating carrier, which is literally the metal carrier. You look on the plane, whose metal is it? That's whose logo's on the plane. That's the operating. Marketing is who's allowed to sell tickets on it. So an online itinerary is defined as someone that basically sells and operates the itinerary. A code share is you have the same marketing carrier. This would be like KLM selling a ticket to fly on Delta. Interline is like where you go online and you decide that you're going to buy 2 separate tickets yourself. So you decide you're going to fly like American Airlines to Miami, and then let's say connect on United Airlines down to Buenos Aires. You take responsibility for both of those separate tickets. There's no agreement or relationship between the 2 airlines. Sometimes, depending on it, you actually have to go outside and check, in through security. So it can be much more onerous as a type of marketing relationship. For price, we have something in the industry that's been done that basically looks at classifying tickets as either business or leisure, or a more precise way to think about this is high yield and low yield. So IATA basically has these fare mappings that can be used to classify tickets as first business and then restricted coach, or restricted coach and other. And we can just think about this as really the high yield and low yield fares. So we did that in our database. We have 2 separate prices. And consistent with what's done in the industry, we took an average fare. We didn't actually use the tickets, the fare information on our tickets. The reason being airlines can't do that. For antitrust reasons, we don't let carriers know what other carriers are selling on price. So we ended up using an average fare that was consistent with, again, what airlines would have if they were building these models. And then, again, just other assumptions. We assumed round price was total price divided by 2. And we included taxes in our models, although we estimated some without them, and the results were very similar. Departure time of day. Some of you may have seen this if you looked in the urban area for departure time of day preferences. But basically, for departure time of day, we did 2 things. We looked at modeling time of day as a continuous function. I'm going to explain why in a minute. And then we looked at this time of day preference in a very segmented way, very fine differences. So where the continuous time of day comes into play is that I could have 2 time of day functions. The one on the left is just basically a lot of indicator variables that you can put in your model. So departure time equals 1 if the flight departs between 10:01 or 10 and 10:59. For instance, that would be an indicator variable. You can also use sine and cosine functions to basically smooth it out. Now, can anybody think of a reason why I might want to smooth out a function versus use a step function? What's going to happen if I'm Delta and I'm an analyst and I'm trying to decide where to put a flight, and I move the flight, in this example, from 10:58 to 11:02? What's going to happen to my probabilities? You think I get a realistic shift, or do I get a jump? Yeah, I get a jump. So one of the issues that happens when we use these step functions in practice is that the analysts get really frustrated. Because they're sitting there and they're doing these timings of flight. They move 2 minutes, and now you're telling me I lose 2 passengers. Versus I can move it from 11:02 to 11:04 and I see no difference. So the smoothing function helps basically eliminate these jumps that can be present with the discrete function and makes more realistic predictions on the back end. So for the time of day classification, the thing we notice with the departure time of day is that you can argue this is one of the most important decisions an airline makes, when to schedule their flights. So understanding customers' willingness to pay for certain departure times a day is very important. Anybody take a recent trip lately out to California? Yeah, so what time did you want to leave to go out to California?
I was coming here, well, it depends on if I was doing a red eye or not.
Okay, depends on if you were doing a red eye or not.
If I was going to do a red eye, it would make sense to go late at night.
Yeah, late at night coming back. You lose a day, but you're basically able to meet your 8 a.m. class, stay longer. Anyone else? What was your choice for either going out or coming back? Yep.
I wanted to leave at noon because I gained 3 hours going back
Okay. Leave at noon because you gained 3 hours coming back.
of that.
Yeah. Okay, let me change the question. Anybody planning your trip to TRB, Washington, D.C.? What time do you want to leave to get up to D.C.?
Bright and early.
Bright and early, because you got the full day when you get there, right? Okay, so what we see on these time of day classifications is exactly what you're talking about. That our time of day preference varies as a function of various factors. It varies depending on what direction I'm going. Am I gaining 3 hours or losing 3 hours? Am I in the same time zone? DC is a very short flight, 6 hours, so I can leave in the morning and get there in the morning very quickly. So what we did is we classified, we came up with 10 segments to basically account for the fact of, which time zone I'm in, which direction I'm going, and is it a short or longer type of flight. And then, similar to what I showed on the red eye, if I'm going out or coming back, we also distinguish between the direction of travel. And if passenger leaving, outbound, returning, inbound, or one way. And day of week, right? If I'm leaving on vacation, I probably want to sleep in a little bit longer before I head to the airport. Versus if I'm leaving on business, I probably got to get there at 7:30 in the morning. So day of week tends to correlate more with business and leisure customers. You can see differences on these preferences by day of week. So looking at the descriptive statistics for our 10, you'll notice that the 600-mile mark really only applies to the same time zone and one time zone. In the US, once we hit 2 time zones, we're above 600 miles, so that's why we don't have it. Why, for my 3 time zones, does the maximum alternatives I have in the choice set, why is that larger, for instance, in the same time zone less than 600? Does that make sense? Thinking about ways to go from DC to San Francisco versus Atlanta to DC. Does it make sense that I would have more options to get? There's more hubs I can go through, right? So this is typically what we see. The longer the distance, the more viable paths that are generated. Because airlines have different hubs, there's multiple ways to get there, other than the nonstop. So our choice set then is a little bit different than that we see, right? In discrete choice modeling class with either Montessori or Garrow. We have, are you kidding me, 150 alternatives for one OD pair? Right? We haven't estimated stuff like that before, right? We're normally looking at 4, 5, 6. So yeah, airline itinerary choice models have a lot of itineraries come into play. So we're going to have to bring the big guns in terms of estimation software to the table to be able to get us to estimate parameters for this. Data representativeness. One of the things that always happens when we talk about airline data is Southwest is not a player. So I mentioned before the data set we have comes from travel agencies. Where does Southwest have all of its customers book its tickets for the most part? Southwest.com. So whenever we're talking about estimations, just a caveat is we have to realize Southwest tends to be underrepresented. However, we do have, like I mentioned before, Priceline.com, Travelocity.com, some of the very price-sensitive channels. So there's no reason for me to believe the results here are going to differ substantially if the Southwest passengers are. Okay, we use itinerary choice models to estimate our discrete choice models. I'm assuming we've all seen these, I'm not going to review it. We talked about the fundamental problem. What's the fundamental solution? So just out of curiosity, has anybody seen methods to control for price endogeneity? Have you heard of this problem before? Because I don't think we really covered it in our courses. Unless it's advanced discrete choice models. Okay, so there's various methods that we can use to control for price endogeneity. One that we're going to do is called a 2-stage control function that uses instruments. Okay, so what is an instrument? Instrument is like this magic, I think of it as